Okay, so this is problem 320, chapter 4 of our book. Um, the question says that we have 800 feet of fencing material to make a pen for hogs. If you have a river on one side of your property, what is the dimension of the rectangular pen that maximizes the area? Okay, so word problems, always word problems starts with that modeling part. This is very important. Modeling part means that you turn the information you have into something mathematically meaningful, and then the problem will transfer to a completely mathematical problem. And then from there, well, you will have your way to find what you're looking for. In this question, first we have to see what is that we are maximizing, what are the functions, what are the variables. So in the modeling part, drawing some pictures are always good. So we have a river next to your uh, land, and you want to make a square, not a square, rectangular pen. So we are trying to make something rectangular. You may say, okay, I can use some rectangles like that, but you right away notice that if you form the rectangle such that all four sides you fence using your material, you're going to uh, basically waste a lot of material for that extra side. Instead, you can use river as one side of your pen. That way, you can put more area inside that rectangular box. So the difference would be here that we only need to have three sides and fence only three sides. Okay. Well, now that I have some idea there, now I will start with identifying, always it starts with identifying the variables. Identify the quantities and then we'll assign variables. So, okay, this is rectangular, so we will have a width, a length. So these are at least two things that comes into mind. So width of the pen and length of the pen. One of the quantities that you have to always pick and bring into your modeling is the value or the quantity that you are maximizing or minimizing, or you're aiming at maximizing or minimizing. Here, we know that we want to maximize the area. So then this in particular is very important, area of the pen. And that at least in this problem, that seems what we have to start our modeling. Okay. Well, always the quantities you have to transform them or find a name or represent them by a variable. Here with I'm going to use W for that. For length, I will use L, and for area, I will use A. That's the first thing. We identify the quantities and then assign variables for them. The second important thing is that find the relations among or between the variables. So in this case, we know that the area of a rectangular shape is always W width times the length L. Okay. Also, we know that this side, I will do with the red, this side, this, and that will be the material of fencing that we trying to use, or we have access to use. And we know that those three sides should add up to 800 feet. So what we know is that there are two widths here. So 2W plus one length must be equal to 800 feet. Yeah. Okay, so these are two relations. And then we know that we want to maximize A when W and L are there. But when you look at A, you right away notice that A depends on two variables. And there is a relation between the variables here that you can use that relation and write one variable in terms of the other one. What I mean, let me just write it here. From here, you see that I can write L as 800 minus 2W. And then if I use that and that together, I will get A is W times 800 minus 2W. And that gives me one function with one variable. A depends only on A. Sorry, W. There's only one variable. And that kind of functions are what we are going to deal with, functions with one variable. Okay? But always remember, when it comes to the maximum optimization problems, it's very important to find the domain of your variables. For a second, you think that, okay, this is, when you look at AW here, AW is going to be, it is a polynomial in W. And the domain of polynomials is always all real numbers. I can put any number I like there. But that is a mathematical domain. We have to find that real situation that we have the domain for that. So let me finding the domain in the domain for W here. Well, what is the domain? Yes, mathematically, I can put everything that I like there, but I don't want to put any random number there, because you see, the W is the length of one side. Yes, so length is always a positive. I am going to include also zero. So the length, by zero length, I mean that, okay, there's nothing there. Okay, so it can be non-negative. So in other words, W is always bigger than or equal to zero. Well, that's a condition that I am introducing at this moment. Also, the same was similarly, L also must be bigger than or equal to zero. Well, that means what? That means that 800 minus 2W, which is L, it must be bigger than or equal to zero. And bigger than or equal to zero, that means that 2W, well, let me just write it this way, 800 is going to be bigger than 2W. And that means that the W is going to be less than or equal to 400. I take it to the other side. I just changed it. So basically, our domain for this problem, not the mathematical domain for this problem is the interval 0 to 400. By doing that, now we are free from the words. We have a mathematical problem in hand, and we are trying to maximize AW, which is this number. By the way, I can simplify that. I can multiply this inside. So minus 2W squared. What did happen? Okay. Sinan, can you hear me?
I can hear you, but we cannot see your screen.
Okay, I'm trying to see if we can. No. Are we back now? Okay. So we are trying to maximize the function AW, which is negative 2W plus 800W on the interval 0 to 400. That's what we are trying to do here. Well, there's a square there. And when you get to this point, that means that you are free of the wording. The problem is now completely mathematical. And maximize means that find the absolute max of this function on this interval. Okay, and for that, we know that we have to find the critical points. Critical points means that I have to find the derivative of this, which is minus 4W plus 800, and then set it equal to 0. And then that will give me W is equal to 800 divided by 4, which is just 200. And note that this is in the interval, is in the interval. If it is not in the interval, we just throw it away and we don't consider it. Okay. What else we need? We need endpoints. Endpoints here, one is W is 0 and W is 400. Now, we have to evaluate the function at these points. A at W. If we use this formula, it is easier to compute these values. So A at 0, so 0 times, what was it, 800 minus, yes, 800 minus 2 times 0, this will be 0. A at 200, this is 200 times 800 minus 2 times 200. And that gives me what? This is 400, 400, 800 minus 400. It is just 400 and times 200, this is 80. And what is the third value? A at 400 is, well, 400 times 0. You check that, that is 0 as well. And we know that when we have a continuous function on the closed interval, well, it is going to have max mean, absolute max mean. Here, as we can see, the max value is given by this. So max of a W on the interval is 80,000. But what is important for us, if you go back to the question, is that we want to find the dimensions of that rectangle. So in this case, we know that the width, which we denoted by W, must be 200. The length, well, just plug it in here. 200 times 2 is 400. 800 minus 400, that's the length, is 400. And while the maximum area for the pen will happen when we choose the width to be 200 and the length to be 400 feet.